Okay, guys, as the bank data seem to be causing a lot of trouble, I found I've created a similar example. I took a data set and I converted the kind of dependent variable column to have the same format as the bank data. Basically, it's another kind of marketing data set. We have lots of demographic information, purchase information, and we have whether they respond and buy from a promotion. And we're trying to predict this buy variable. There's also a little bit of junk. There's the date column, which really isn't going to be useful. And we've got two columns here. You notice that these columns, all the variables are constant. And this column I've called the silly column, and that's obviously one that's going to blow up the technique, but I'm just going to kind of keep it in as an example. And we also have the ID column, which again doesn't provide any useful information. But assume that I've been kind and told you to get rid of the ID column. Okay, so the first thing we want to do is we want to identify the code that would be most useful for us. And this is taken from the chapter 6 code, and this is the code for predicting logistic regression, which is the problem we have. We've essentially got to do 100 runs, and in the homework we've got to predict for the bank data, and in this example I'm going to have us predict in the marketing data. So this is really just showing you how to take a piece of code, my code, and then adapt it. It's also, this example is very similar to the bank data in the homework, probably more similar than the example in chapter 6, so it should help you with the homework. Okay, so first of all, we read in the data. And of course, we always want to look at our data, so we got view the data. And we can see here all the data, and we can see the columns that, for example, that we want to get rid of. And let's go back to this. We can also look at the column names. And again, that will tell us we're in the right format. So we ideally want what we're trying to predict as a factor. We also notice my silly column is a factor with nearly 40 levels, which is probably not going to be particularly useful. The customer date is a factor with 663 levels, which again is not going to be particularly useful. But we'll kind of keep them in for the moment. So what we want to do is, if we're kind of adapting code, let's just kind of copy, make sure that we have all the relevant libraries at the top. So let's just run all the library information, including the analytics aid function. And let's just kind of copy the code. Now, what we want to do is we want to kind of remove anything that's related to the old example. So we know that the old data set was called auto3, and our new one is called mdata. So let's just do the find, which is Control F. And so we're going to find auto3. I'm just going to replace with mdata. So let's just do replace, 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 replace. And we don't want to go back to the top, the original example. So we've just replaced all of our examples with mdata. Now, let's just kind of go through the actual rows and just see if there's anything which is specific to the previous problem. So the first 4 rows are now fine. This is mdata, and these are just, we're setting up the number of runs and base values for the accuracy in the tables. The training and the sample, these are just working on the size of the data set, so we don't need to change them. But get to this. So here we create a glm.auto, logistic regression model for auto, and we have our dependent variable is miles per gallon, and we've had all our independent variables added. So let's just now call this glm.mark, and let's go to our mdata. And the dependent variable here is the buy. So we have buy. And let's just say we don't want to type in all the other variables, but we assume that everything else is a useful predictor. And we go kind of through the row, M data, nothing else here is actually relevant to the previous data set. Now let's go to the prediction, the glm.pred. And again, we go through, we've got a round function for rounding a probability. We have predict.glm, which again is not specific to the data set. glm.auto. That's from the previous example. We changed that to glm.mark. And we're putting in our test data, the minus train, but this time we don't have to do anything else because we've changed the test data from auto to the test data for kind of the M data. The next line is the evaluation, my evaluation function. And here we're comparing the M data. We're comparing all the tests. The test is just anything that's not in the train minus train. Aha, miles per gallon 0.1. That's certainly not in our data set. And in fact, our dependent variable, of course, is going to be by. And then the accuracy, this is all just to do with my function, and the table is to do with my function. So basically, we only had to change a few things. Now let's just see if it works. So let's just load in the data again. We're setting the ID column to null. Now, when you're going through particularly somebody else's code or your own code, it's always good to check what happens at each line. So we've got n equals the number of rows in M data. Just check it gives us something useful. 2240. So we have 2,240 rows. Now, one thing I always like to check with my data is, are there any NA values? And let's just sum these. Okay, so to remove the missing data, we're just going to have to do M data. And I've done this multiple times throughout the code, so it's in my notes. You can kind of just see how I've done that. Or you could just look at this example. So we do is.na M data. And so that would basically, we'd want the row sums of this. So for each row, we want to see the sum of the missing data. And we only want to keep the rows with no missing data. So we have equals 0. And then we want all the columns. Now you could actually, I've been a bit overly complicated. There's actually a command in R called complete.cases. And you do complete.cases M data would do the same as, exactly the same as this. So let's just kind of copy that, run this, and put this in here. Okay, so now let's run through our code and just kind of go through each row in turn. This is really important that you understand what you're doing. I keep mentioning this, but we understand what we're doing as we go along. So each time we run a code, just see what happens. So we've got 2,216 rows of data. These are simple assignments. One setting the number of runs, one setting the base values for the accuracy and for the tables. Okay, now anytime you do a loop, if something's going to crash in the code, then it's going to crash again and again and again and again, and you're just going to get in a mess. So with a loop, what I would always say is just run it manually the first time. And you do that by setting it to equal the first value. So I equals 1, and this will now put you in the loop for the first time. And again, as I said, it's really important every time you run a line of code, just see what you've created. So n sample, this is just half the value of n. So we're selecting half the values for the train. Train, this actually is the actual training data we select. So this is the actual half rows that we've randomly selected. Now the next row actually runs the logistic regression. Now this is going to be a mess because we have some pretty messy columns in there, which, you know, let's just have a look at this. Okay, And you really want a continuous for regressions or logistic regressions. You want continuous variables, or you want categorical variables with only a few categories. Because we can't have here we're having a dummy value for every single date with DT customer. So this is just messing everything up. We've got all these like additional dummy variables, one for each date. So let's just kill this guy off. Okay, so we've set it to be null. Now what we're going to have to do really is we're just going to have to go through the whole, you know, code again. Set I equals 1 and kind of go through this process of creating the regression again. So let's now go through it again. We know what these guys do and they're not dependent on the data, so let's just work through that. Now let's try our logistic regression again. So let's just see what we get. Oh, we're still getting useless information. Now we look here, we say Z contact cost and Z revenue crash. They give us NAs. Now why is that? Well, we noted before, if you see something like this, then just check what's in the column. Here we see cost contact and Z revenue. They're the same value for every row, so they're not really giving us any useful information. So we'll remove those. And the silly column is just a silly column I created to show you how to deal with a column with bad data. So we're going to remove Z cost contact, Z revenue, and the silly column. So and let's just set the silly column to be no. Okay, now take 3. So, even a simple problem like this, the process can be hard. This is why analytics professionals earn a lot of money. And again, let's just do I equals 1 and start going through this code again. So let's kind of go all the way down and create our regression model, logistic regression model. And you can see here now we have nothing really dubious. We maybe have, for example, marital status. None of these are significant. None of the levels are significant. The kid home is not significant. One or two of these like purchase values is not significant. So we may actually want to run a stepwise regret. If I was doing this for the project, we might want to run a stepwise regression, or we might want to remove the non-significant variables. But for the moment, it's for homework. Just let's go on and do the predictions. Okay, so we've got the glm.pred and see what it kind of creates us. Now, what this code does is it's basically for all of our test data, mdata minus train, which is the test, it predicts the probability of a success. And then it rounds that to give a 0 if we predict a failure and a 1 if we predict a success. So we'll say a 0.3% of a success will be to 0, a failure. A 0.7 success will be round to 1, which will be a success. Okay, let's try and run this code. Oh, and it crashes. Now, what the problem is I think this was just from a kind of a test data set because some junk has been added into it, and basically we have 2 marital status levels. One is absurd, and the other is YOLO. I think I'm not up on slang what that means. I'm sure some of you people might know. But basically what that means is that we have some factor levels in our test data set that are not in the training data set, and that breaks our model. Now, that can kind of often happen if you've got a factor with lots and lots of levels, um, and it can be problematic. So for this time, let's just kind of remove marital status. It's just got too many factor variables that could kind of crash this. So let's just put, and there are ways of dealing with this, but for the homework, anything that's causing problems, just remove it. Okay, so now let's do the whole thing. And again, we're going to go through I equals 1. And we're going to get through, we got up to the glm.pred. And let's just see what it gives us. It gives us the ones or the zeros. So 0 if we predict failure, and 1 if we predict 1. Okay, so the next thing we do is we're going to compare our predictions with the actual held out data in the test data set. So this is these guys here, which are the no's and the yeses. And we want to compare them with our predictions, which are the zeros and the ones. And this third value, you could actually look at the code. This is just the value for a success. So if yes is a success, then this would be a yes. Now you should notice a problem here. We're trying to compare yeses and nos with zeros and ones. So that could be actually a big problem. Now I did this in chapter 8, and this I think has caused the most issues, but we want to change the GLM predict from zeros and ones to yeses and nos. Now, of course, if you're really stuck on your homework, what you could have done is you could have gone back to your Excel spreadsheet and just replaced all the nos and yeses with zeros and ones. But let's just kind of do it in the code here. So let's just glm.pred equals, and you'd use a function called if-else, glm.pred equals 0. So if it's equal to 0, then we're going to have it no, or otherwise it's going to be a yes. And let's run that little function. And now let's run the class eval. So we're comparing the no's and yeses in the held out test data with all of our actual now predicted no's and yeses. So let's just run that, make sure my code works, and just see what I've created. Okay, I think it's because I actually run it twice. So let's just kind of go back and run it again. Okay, that's much better. So it's a no if it was previously 0, and yes if it was previously a 1. We run my class eval function, which now both the held out test data and my predicted data are no's and yeses. It works perfectly but oh, it still crashes. And why is the reason for that? That's because we didn't change this, the success value, to be the success value in the data. So actually, this is the most common problem on the homework, and I just actually blundered into it myself. So now let's see what we have. And we get the proper evaluation. And what we do is, we're calculating accuracy, we're adding accuracy up and then eventually divided by 100. The table command just has the kind of success table. And whoops, we didn't change this from MPG 01 to by. So now we have our table. And there we have our predictions versus our actuals. And then we let this we can run through this 100 times, and then we'd add the table and add the accuracy, and then we divide by 100 to get the average. So let's just kind of go now from the beginning, run through the data, and we get our accuracy and we get our actual predictions. Now, I remember in the question, I might ask you other things besides accuracy, hint, hint. But look, last time we did the eval function, we noticed it gave a lot of different values, and it gave them in exactly the same format as accuracy. So it makes sense that rather than whatever we do for accuracy, we could just do for one of these. So say let's just do for recall. Every time we do something with accuracy, we just do it with recall. So we set a recall value to 0. We now add the actual recall returned by glm.eval. So just add another line for recall. And again, we've divided accuracy by 100, so we need to do the same for our recall value. And let's try running the code again. Okay, so now we have an accuracy, average accuracy, an average recall, and kind of an average table. And so for things like recall specificity, precision, you could do what I did and add them extra, or you could actually just calculate them using the definitions in chapter 6 from this table. Either would actually be fine for the homework. Okay, so as I said, I realize this is not easy. This example is closer to the homework example. I also hope I've given you, when I keep telling you to test code line by line, that's the only way to be successful in these things. I hope this little tutorial actually helps you, give you a bit of practice doing this, which will actually help you in your project.